Fluid Year 12, here's a quick video looking at a harder differential equation question that Liam's asked me to go over. Now, I think most of you were here in class when we did it, but I don't remember if everyone was watching when I went through it or not. It's a pretty standard DE question, as long as you spot the integral, until we get to the last bit, which is to show that the number of organisms never reaches 48, no matter how large T becomes. So I should have said the whole thing is a question about bugs yet again, and the population of bugs in a population, bugs or organisms, if you're being scientific. So we start off in the usual way. The only thing we know how to do is to separate the variables. So pause the video, go ahead and do that, and then come back. Now we've got two conditions that we're going to work in once we've done the initial integration. We've got an initial condition when t is 0, x is 10, and then the next one when t is 1, x is 20. We have to show that the constant k pops out as this, and then we'll do the last bit. So it's not too bad, so give it a go, and then I'll walk through it. So here's the first bit. We've got dx by dt is equal to this. Separating the variables gives me 1 over x dx is equal to e to the negative t over k plus e to the negative t. I'm going to integrate both sides. Now, don't do anything crazy with the right-hand side. Even though it looks hard, if you look at it for a minute, you'll spot that we've got our happy pattern of having a thing in the denominator, an expression in the denominator, and the derivative of that function sort of in the top line in the numerator. So that means that we're going to have a natural log, and it's not going to be too bad at all. So on the left-hand side, as we often have with DEs, we get the natural log of x, and on the right-hand side, we'll try this first. So the natural log of k plus e to the negative t. Now look at that. Think about what happens when you differentiate. It just about works, but we're going to have negative e to the negative t. We don't want that. So we have to multiply the whole thing by a negative and add on our arbitrary constant of integration. I'm just going to do one thing here before we play with the logs. And that's that. So put that back into one log. Leave that like that. Now the next thing I'm going to do is I'm going to drop the absolute value signs, because I find they confuse my brain when I don't need them. The reason I don't need them here is that e to the negative t is always positive, and we're adding k to it. So we might as well just write it like this. The natural log of k plus e to the negative t to the negative 1 plus c. So that was all slightly optional, but there you go. Now, the next step is to say I'm going to do e to the power of both sides, giving me this. So x is equal to e to the power of this, and that's equal to a times e like that. And then the last step is to say, well, hang on, there's not much point having e to the power of a natural log now that we've seen the pattern. So it's going to be just a times k plus e to the negative t to the power of negative 1. So that gives me x is equal to a over k plus e to the negative t. And now we're ready to do the rest of the problem. And we've got it into quite a nice, simple form. So our initial condition is t is 0, x is 10. That gives me 10 is equal to a over k plus e to the 0. 10 is equal to a over k plus 1. Giving me a equals 10 times k plus 1. So that's good, that's one of them done. We can now substitute that back in to our expression for x. So let's see where we'd got to with x. Right, so x was up here, was equal to that. So x is equal to 10 times k plus 1 over k plus e to the negative t. Now the next step is to use this condition. When t is 1 and x is 20, we want to show that k is equal to 1 minus 2 over e. Now just be really careful when you're doing a show that question that you don't just use your brain and skip a whole lot of steps, because that's not what show that means. In this case, it's not too hard to do that though. So substituting in, we get 20 is equal to 10 times k plus 1 over k plus e to the negative 1. Just cleaning that up, giving me 20k plus, I'll just write it how it is here, 20e to the negative 1 is equal to 10k plus 10. You can clean that up where you want to. So that gives me 10k equals 10 minus 20 over e, dividing through by 10, k equals 1 minus 2 over e as required. So that's that next bit done. Let's go back to the question and see what's left. All right, so we've done the first two, so that's 8 marks, all good, and hopefully quite enjoyable maths along the way. And now we're going to show that the number of organisms never reaches 48. So this is the cool bit where we have to think about limits. So let's go to, I'll go to a clean page for this. Right, so where we've got to is that we showed, we showed what k was. So k is equal to 1 minus 2 over e, and x is equal to 10 times k plus 1 over k plus e to the negative t. So we can take that value of k, we're going to substitute it in and look at the properties when t gets very, very large. So it's 1, what have we got, minus 2 over e, minus 2 over e plus 1 over 1 minus 2 over e plus e to the negative t. So cleaning up here gives us this 20 minus 20 over e divided by 1 minus 2 over e plus e to the negative t. Now we can work with the over e stuff, but I don't really like it. So we're going to go through and we're going to get a common denominator of e for both the numerator and the denominator and do some cleaning up before we think about what to do next. Except that in the back of my mind is this picture. This is the picture of e to the power of t, or the graph of e to the power of t, and this is the graph of e to the negative t. So we know that e to the negative t is going to go towards 0 when we've got a very, very big number. So that's going to help us here. So here we have 20e minus 20 over e divided by e minus 2 plus e times e to the negative t over e. So that equals 20e minus 20 divided by e minus 2 plus e to the negative t plus 1. There are a number of ways to do this problem, okay, but here's one of them. So this is 20 in the numerator, 20 times e minus 1 over e minus 2 plus e to the negative t plus 1. Now one thing you could do is, in desperation, you could grab your calculator and take a really big value for e and see what you get when you put this in. But the other way to do it is to say that the limit as t goes to infinity of e to the negative t is equal to 0. And you could draw the graph to show that what's going on. And if you think about it for another second, hopefully you'll see that if we have e to the negative t times e, it's also still going to be equal to 0. So what does that mean? Well, it means that when t gets very big, this denominator is heading for a fixed value, which is e minus 2. So what we're going to say now is that the limit as t tends to infinity of x is equal to 20 times e minus 1 divided by e minus 2. Okay, because this is not changing. This thing here is not changing when t gets enormous, and this thing is heading to a tiny, tiny number. So if you now grab your calculator, there's no other way to do this bit, and you type all of that in, you will get very happily the following number, 47.84 da 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 da, which is less than 48. So no matter how big t gets, the number of organisms in the population will never reach 48. There you go. Hope you enjoyed that. If you have got any last minute questions like that, just flick me an email today and I'll see what I can do. I'll either do some quick solutions for the whole class or I'll do another wee video. Thanks for watching and good luck with the last bits of revision today.